On the slopes of Mauna Loa in Hawaii, where the sky is often clear and the ocean winds thin the atmosphere into crystal transparency, a pair of robotic telescopes were quietly sweeping the heavens. These instruments, part of the ATLAS project, short for Asteroid Terrestrial Impact Last Alert System, were not built for glamour. They were designed as watchmen, scanning the night for faint dots of light that might, one day, signal doom. Their primary task was to catch asteroids on a collision course with Earth, buying humanity precious days or weeks of warning. But in early 2020, one of those telescopes detected something that would ripple across the scientific community and stir imaginations far beyond astronomy. The object was faint, barely visible against the background of stars, but its movement stood out. Over successive nights, as software linked observations into a coherent track, the pattern became clear. The body was racing in on a steep trajectory, not along the familiar ellipses of comets and asteroids born in our solar system, but on a hyperbolic path, a track that would never close into a loop. It was as if a messenger from the deep void beyond the sun's dominion had stumbled briefly into our neighborhood, only to depart forever. Astronomers gave it the temporary designation C/2019 Q4, later renamed 3I/ATLAS, marking it as the third confirmed interstellar visitor after Oumuamua in 2017 and Borisov in 2019. At first glance, 3I/ATLAS seemed like a comet. Its diffuse coma, a hazy envelope of gas and dust, hinted at volatile ices sublimating under the sun's heat. Yet something about it felt different. Its brightness fluctuated oddly, sometimes flaring and then fading more quickly than expected. Its trajectory, when plotted with precision, revealed a velocity that was simply too high for any object native to our system. Even if it had been nudged by the giant planets, no gravitational interaction could explain its inbound speed. This was the smoking gun. Like a stone skipped across a pond, 3I/ATLAS had not been born in our waters. It came from elsewhere, ejected from some unknown star system long ago, cast adrift on a million-year journey across the interstellar gulfs. For the astronomers who first processed the data, there was a moment of disbelief. It was rare enough to catch comets from the far reaches of our own Oort cloud. To see something that originated light years away was like a fisherman casting a net into the ocean and hauling up not a local fish, but a creature from a completely different sea. Suddenly, the dry business of nightly survey work took on a feeling of cosmic drama. Here was an emissary, a relic of another sun, another system, perhaps another story of planetary formation that had unfolded in parallel to our own. But the discovery was bittersweet. By the time the world's telescope swiveled to track it, 3I/ATLAS was already breaking apart. Unlike Borisov, which offered months of observation, or Oumuamua, which passed relatively intact though enigmatic, this newcomer seemed fragile. Its nucleus disintegrated under the stresses of solar heating and rotation, reducing what might have been a rare chance at pristine interstellar material into a fading cloud of dust. The timing was cruel. Just as astronomers were preparing instruments to probe its composition, it began to vanish before their eyes. Yet even in its decay, 3I/ATLAS spoke volumes. Its very existence confirmed that interstellar debris might be more common than once imagined. 3 such detections in just a few years suggested we are bathed in a slow rain of alien wanderers. Before 2017, such a thought was speculation. Now, it felt undeniable. The fact that Atlas, a system built to protect Earth from cosmic hazards, had stumbled upon something so profoundly alien seemed almost poetic. Humanity, always watching the skies in fear of destruction, had instead caught sight of a fleeting visitor, a reminder that our solar system is not isolated, but open to the endless highways of the galaxy. The announcement of its discovery sent ripples beyond academic circles. Headlines proclaimed another interstellar visitor detected, and comparisons to Oumuamua reignited debates about what these objects might represent. Were they merely natural fragments, pieces of shattered comets expelled from their birthplaces? Or could they, as some more speculative voices dared to ask, be artificial, spacecraft or probes lost to time, wandering endlessly between stars? Most scientists dismissed the latter, but the very fact that humanity now had repeat encounters with such objects stirred imaginations in ways no dry data set could contain. For the astronomers on Hawaii's slopes, however, the reality was humbler and more urgent. They had discovered something that could never be captured, never be returned to, only observed for a few precious weeks before it slipped back into the dark. Their instruments were not designed to chase down the rarest travelers of the cosmos, but for a brief moment, they became the stagehands in a drama written billions of years ago in some distant star system. The Atlas telescope, meant to be Earth's early warning sentinel, had by chance opened a window into the vast traffic of the galaxy, and through that window, humanity glimpsed 3 I/A TLAS, the ghostly trace of a traveller from the stars, here for an instant, gone forever, yet changing the way we see our place in the universe. In October of 2017, a faint streak of light passed through the telescopes of the Pan-STARRS Observatory in Hawaii. At first, it looked like countless other objects astronomers track each night, a minor curiosity destined for cataloguing and obscurity. But within days, orbital calculations revealed something extraordinary. The object was not bound to our sun. It was the first ever confirmed interstellar visitor, given the name Oumuamua, a Hawaiian word meaning scout or messenger from afar. Its trajectory was hyperbolic, a one-way path through the solar system, and its velocity was far greater than any comet or asteroid native to our celestial neighbourhood. Humanity, for the first time, had proof that fragments from other star systems could and did enter ours. Oumuamua was a puzzle from the start. It showed no visible coma, no trail of dust or gas like a typical comet, and yet its motion betrayed a faint acceleration, as if some invisible force was nudging it along. Some scientists argued this was the result of outgassing too subtle to detect, while others speculated on exotic explanations, ranging from hydrogen ice to nitrogen shards blasted off an exoplanet. But the most tantalizing idea, floated by a handful of respected voices, was that it might be artificial. Could Oumuamua have been a fragment of alien technology, a probe adrift between the stars? The idea was controversial, but it captured the public imagination. Here was a mystery, with no clear resolution. By the time telescopes were trained on it, Oumuamua was already fading into the dark, too distant to study further. All that was left were questions, destined to haunt the scientific community for years. Barely 2 years later, in 2019, another interstellar traveller appeared, this time unmistakably a comet. Discovered by amateur astronomer Gennady Borisov in Crimea C/2019 Q4, Borisov looked much more like the icy wanderers we knew, a nucleus shrouded in gas, with a long tail stretching into space. Yet its speed and trajectory confirmed it was not one of ours. This was the second interstellar visitor, and unlike Oumuamua, it offered months of observation. Spectrographs revealed water vapour, carbon monoxide and other volatiles, suggesting Borisov was chemically similar to comets in our own system. This gave scientists their first solid evidence that planetary systems elsewhere in the galaxy produce the same kinds of icy debris as ours. Where Oumuamua had baffled with its strangeness, Borisov reassured with its familiarity. 2 visitors, back to back, so different yet so revealing. Together, they suggested that the galaxy was full of such fragments, ejected during the chaotic birth and evolution of alien star systems. By the time 3 I/A TLAS arrived in 2020, astronomers were ready. Oumuamua had taught them to expect the unexpected, to look for oddities in motion and brightness. Borisov had shown that interstellar comets could, at least in principle, be studied in detail if caught early enough. The scientific community had shifted from astonishment to preparation. Telescopes across the world were tuned to respond more quickly. Survey software was refined to flag unusual trajectories sooner. The shock of the first encounter had given way to a sense of anticipation. If it happened twice, it could happen again. When Atlas detected the faint trace of C/2019 Q4, later renamed 3I/Atlas, the news spread quickly through astronomical networks. Almost immediately, researchers began drawing comparisons to its predecessors. Would it be strange and enigmatic, like Oumuamua, or comfortably comet-like Borisov? The answer, frustratingly, was somewhere in between. 3I/A TLAS seemed to bear a coma like a comet, but it fractured so quickly that its secrets slipped away almost as soon as they were glimpsed. Unlike Oumuamua, there was no debate about its hyperbolic nature. It was unmistakably interstellar. Unlike Borisov, there was no extended window of study. It was fragile, fleeting, almost ghostly. Still, the very act of finding it proved a crucial point. Humanity was no longer blind to the traffic of the galaxy. These were not once-in-a-millennium events, as some had assumed after Oumuamua. Within 3 short years, 3 separate interstellar objects had been tracked. Statistically, this was astonishing. It suggested that interstellar wanderers pass through our solar system far more often than previously believed, perhaps dozens every year, slipping past unnoticed. What had changed was not the cosmos, but us. Our eyes had sharpened, our instruments had become faster, more automated, more capable of distinguishing the subtle arcs of alien debris from the familiar dances of local asteroids. The Atlas discovery was, in many ways, the culmination of a shift in mindset. Before 2017, few astronomers seriously expected to find interstellar interlopers. The possibility existed in theory, but the odds seemed remote, the galaxy too vast, the opportunities too slim. Oumuamua shattered that complacency. Borisov confirmed it was not a fluke. And by the time Atlas spotted its own interstellar guest, the scientific community was primed not with disbelief, but with readiness. They had protocols for rapid response. They had teams eager to analyze spectra, measure trajectories, and run models. For the first time in history, Earth's astronomers were operating with the expectation that the stars would occasionally send gifts or riddles our way. Yet this readiness only deepened the sting of 3I/ATLAS's disintegration. The lessons of Oumuamua and Borisov had prepared humanity to ask the right questions, but not to catch answers before the opportunity slipped away. If Oumuamua was the strange scout and Borisov the reassuring twin, then 3I/ATLAS was the reminder that cosmic visitors are fragile, fleeting, and easy to lose. Each one, whether it lingers or fades, writes another line in a story we are only beginning to understand, that we are not an isolated solar system drifting alone, but part of a galaxy in motion, where fragments of distant worlds cross paths with us more often than we ever dared to imagine. The path of an interstellar object is written not in poetry, but in mathematics. When astronomers first begin plotting the motion of a new discovery, they calculate its orbit against the backdrop of the solar system. Where is it now? Where was it yesterday? And where will it be tomorrow? From just a handful of positions, they can project a curve, usually an ellipse, which shows the familiar closed loops of comets and asteroids bound to the Sun. Every rock, every icy body native to our system follows this eternal dance, circling, sometimes stretching far into the dark, but always returning. That is the natural order. So when the data for 3I/ATLAS began to coalesce, it was the shape of its trajectory that set alarm bells ringing. This object was not following an ellipse, it was following a hyperbola. A hyperbolic orbit is a mathematical fingerprint of freedom. Instead of curving back toward the Sun, the object's path bent around it only once before shooting away into the galaxy, never to return. The numbers spoke clearly. Its eccentricity, the measure of how stretched an orbit is, was greater than 1. That single fact sealed its fate. Nothing born in our solar system could move in this way, not unless it had been hurled out by a titanic gravitational slingshot. But even then, such an object would have had to begin close by and linger long enough to betray its origin. 3I/ATLAS did not. Its inbound speed alone, tens of kilometers per second faster than any local comet, proved it had been traveling for ages, long before the Sun ever crossed its path. Scientists ran the calculations over and over, testing against perturbations from Jupiter and Saturn, against uncertainties in its measured position, against the influence of non-gravitational forces like outgassing. The answer did not change. The inbound velocity of 3I/A TLAS at infinity, its so-called V infinity, was positive, meaning it came from outside, already moving faster than the Sun's gravity could ever contain. It had fallen into our system not as a child returning home, but as a stranger simply passing through. If gravity is a cage, the Sun's pull is a strong one, but not strong enough to catch this traveller. To appreciate the oddity of such a path, one must imagine the solar system as a series of concentric highways. Local comets speed along the outer lanes, looping around in long ellipses that take them out toward the Oort cloud before swinging back in. But a hyperbolic visitor is like a car tearing across all lanes in a straight shot, coming from nowhere on the horizon and disappearing to the other side before anyone can react. The angle of approach, the steepness of its curve, even the direction it came from, all confirmed that 3I/A TLAS was not one of ours. It had entered from the outer dark, perhaps ejected from some alien sun millions or even billions of years ago, and by chance its path intersected with our tiny island of planets. This was not speculation. The orbit was reconstructed with high precision thanks to the rapid alerts from ATLAS and the follow-up observations from observatories worldwide. Astronomers watched as it accelerated toward perihelion, the closest point to the Sun, its speed peaking as it whipped past before slowing again on its way out. Nothing about the trajectory hinted at capture. If anything, the orbit confirmed that the solar system had no hold on it. By the time it left, it would be heading into interstellar space with nearly the same velocity it had arrived with, as if the Sun's great mass were little more than a speed bump along its ancient journey. But perhaps the most profound proof came not from the mechanics of the orbit, but from what the orbit implied. If 3I/A TLAS could not be bound to the Sun, then its true home lay elsewhere, among the stars. Somewhere in a system we will likely never identify, a planetesimal or cometary body had been dislodged long ago, cast outward by gravitational encounters or the violent early history of a planetary nursery. Once freed, it drifted into the galactic tide, joining the uncountable billions of icy wanderers that roam between stars. For eons it travelled, invisible and unremarked until fate brought it across our telescopes. Its path was not random, but inevitable. In a galaxy with hundreds of billions of stars, interstellar debris is as common as dust, and every so often Earth becomes a witness to their passage. Astronomers could trace the trajectory backward across the sky, projecting where it might have come from. But here, the limits of knowledge intruded. Small uncertainties in position ballooned into vast cones of possibility as the clock was rewound. The object could have come from almost anywhere in the galactic neighbourhood, perhaps from a young star system only a few dozen light-years away, or perhaps from one long since dispersed into the cosmic background. No clear parent star could be found. This anonymity only deepened the mystery. The galaxy had sent us a visitor, but not a calling card. Yet in the cold numbers of its orbit, there was a kind of awe. Here was a tangible link between worlds. Oumuamua had been the first, Borisov the second, and now 3I/A TLAS the third. Each had followed a hyperbolic path. Each had written proof of its alien birth in the mathematics of motion. Each one reminded us that the solar system is not a sealed bubble, but an open crossroad where the highways of the galaxy occasionally intersect. The Sun is just one gravitational well among billions, and its walls are not high enough to keep out the galaxy's wanderers. For the astronomers who pored over the data, the confirmation was both thrilling and frustrating. Thrilling, because they were watching the very equations of Newton and Kepler reveal a truth larger than human history. This object was not ours. Frustrating, because they knew it could never be chased, never be slowed, never be studied up close. It was like standing on the shore, watching a message in a bottle drift past on a current too swift to grasp. The hyperbolic arc of 3I/A TLAS was a signature, yes, but it was also a farewell. It announced its interstellar origin with certainty, but it also guaranteed that we would never see it again. In the end, it was the trajectory itself that told the story. A path unbound, a speed too great, a curve too steep to be held. Proof written in starlight and motion, undeniable in its clarity. 3I/A TLAS was not a child of the sun. It was a stranger from the stars, passing through our system on its way to nowhere we can name, carrying with it the secrets of another world we will never touch. Its orbit was not just a line on a graph, but a cosmic declaration that we are not alone in the galaxy's traffic, that fragments of alien systems brush past us in silence, and that every so often, if we are watching closely enough, we will see them go by. When astronomers finally confirmed that 3I/A TLAS was interstellar, the next great question immediately presented itself. What exactly was it made of? The heart of the mystery lay not just in its trajectory, which clearly marked it as a stranger, but in the secrets of its physical composition. Every comet, every asteroid, every icy fragment carries with it the fingerprints of its birthplace. By studying the light reflected from these bodies, splitting it into spectra, measuring the lines that betray the presence of water, carbon, oxygen, or more exotic compounds, scientists can piece together the history of its formation. With 3I/A TLAS, the hope was tantalizing. Here was a messenger that might carry within it the chemistry of another solar system, a set of clues to how alien worlds are born. But as with so many stories in astronomy, the universe had other plans. The first step in unraveling 3I/A TLAS's composition came through spectroscopy. Telescopes trained on the object gathered its light and dispersed it into rainbows of data, hunting for absorption features, those telltale dips where atoms and molecules soak up specific wavelengths. Early attempts suggested that, at least superficially, 3I/A TLAS resembled the comets we already knew. Its coma, the diffuse envelope of gas and dust surrounding its nucleus, hinted at the sublimation of volatile ices under the warmth of the sun. Hydrogen cyanide, carbon monoxide, and water vapor were among the suspects, just as they are in ordinary comets. On the surface, this seemed to align it more closely with Borisov, the interstellar comet observed in 2019, than with the enigmatic Oumuamua, which had shown no coma at all. But almost immediately, peculiarities crept into the data. The brightness of 3I/A TLAS fluctuated wildly, sometimes growing stronger, then fading unexpectedly, even when geometry alone could not explain the changes. Unlike most comets, whose activity increases smoothly as they approach the Sun, 3I/A TLAS seemed to sputter and falter, as though its material was not being released evenly. Some nights it blazed brighter than expected, then fell off dramatically, leaving astronomers to wonder if it was shedding material in bursts or if its surface was already unstable. The inconsistency made it difficult to pin down its true size. Was it a modestly sized comet fragmenting under stress, or a larger body concealed behind shifting clouds of debris? The problem deepened when high-resolution images hinted at elongation in its coma, as if the nucleus itself might already be breaking apart. Unlike Borisov, which held together long enough for extensive study, 3I/A TLAS seemed fragile, crumbling almost from the moment it was discovered. If it was composed of loosely bound ices and dust, then solar heating may have been tearing it apart from within. Yet this fragility itself raised questions. Why would an interstellar object, having survived untold eons in the cold of interstellar space, disintegrate so quickly in our sun's relatively mild embrace? Was it already weakened by some ancient collision, or was it formed from material more brittle than the comets of our own system? Comparisons to asteroids complicated matters further. Unlike comets, asteroids are rocky, lacking volatile ices to drive activity. Oumuamua, with its lack of a coma, was at first thought to resemble an asteroid. though later theories suggested it might have been composed of exotic ices like hydrogen or nitrogen, sublimating invisibly. 3I/ATLAS, by contrast, seemed unmistakably cometary, yet its behaviour was erratic. It neither followed the predictable curve of a stable icy body, nor the inert silence of a rocky one. It occupied a liminal space, echoing familiar categories but never fitting neatly within them. This refusal to conform is precisely what made it so tantalizing. If 3I/ATLAS truly was a comet from another star, then its peculiarities might reflect the unique conditions of its birthplace. Perhaps it condensed in a system richer in certain volatiles, producing a body more fragile than ours. Perhaps its long exile in interstellar space altered its chemistry, with cosmic rays slowly baking its ices into unstable forms that crumbled when sunlight returned. Its fluctuating brightness might have been the last gasp of a body long past its prime, collapsing under stresses it could no longer withstand. Yet, without a stable nucleus to study, much of this remains speculation. The spectral data, while valuable, were blurred by the object's rapid disintegration. By the time instruments gathered enough light to search for subtle molecular signatures, much of the nucleus had already dispersed into a cloud of dust. It was as though a priceless book had been dropped into water just as scholars began to read it. The ink blurred, the pages crumbled, and only fragments of meaning remained. Still, those fragments mattered. Even in its death throes, 3I/ATLAS reinforced a pattern. Borisov had shown that interstellar comets could look strikingly familiar, while Oumuamua had defied categorization altogether. 3I/ATLAS straddled the line, echoing both. It displayed a comet's coma, yet dissolved with a fragility that felt anomalous, while its fluctuating brightness evoked the enigmatic irregularities of Oumuamua. Taken together, the trio painted a picture of diversity. The galaxy's debris is not uniform but wildly varied, shaped by the quirks of alien chemistry and history. Some are sturdy enough to survive, some are strange enough to bewilder, and some, like 3I/ATLAS, are too fragile to hold on to their secrets for long. For astronomers, the inconsistencies in 3I/ATLAS's brightness were not just curiosities but warnings. They revealed how difficult it is to study such visitors in real time, and how little margin for error exists. A fragile interstellar body may give only days or weeks of useful data before vanishing forever. If humanity truly hopes to understand them, not just glimpse them, we will need instruments and missions ready to respond instantly to capture their spectra and their structure before time runs out. 3I/ATLAS may have slipped through our fingers, but it left behind a lesson as clear as any spectral line. The galaxy is sending us pieces of its worlds, but they will not wait patiently for us to learn their secrets. From the moment astronomers first locked eyes on 3I/ATLAS, one unsettling fact became increasingly clear. It was not a stable, solid traveller. Unlike Oumuamua, which managed to streak past our sun and exit the solar system relatively intact, 3I/ATLAS did not survive long enough for scientists to study it in the detail they had hoped for. Its discovery carried all the hallmarks of promise: a second confirmed interstellar visitor, another chance to answer the nagging questions that Oumuamua left behind, and perhaps an opportunity to finally pin down what these wayfaring objects really are. But within weeks of excitement, it began to unravel, literally. By April 2020, telescopes that had been eagerly monitoring the object reported something strange. 3I/ATLAS was brightening much faster than expected. In fact, at its peak it flared to a brightness so great that backyard telescopes could catch it. To casual stargazers, it was simply a beautiful cometary display. To professionals, the sudden brightening was not a sign of opportunity, but of distress. It indicated that the object's nucleus, the solid core that holds comets together, was likely disintegrating. The data soon confirmed the suspicion. The Hubble Space Telescope, along with ground-based observatories, captured images showing that 3I/ATLAS was not a singular point anymore, but a stretched out smear. In subsequent observations, that smear resolved into a cluster of fragments, drifting apart like embers carried by cosmic wind. What had been thought of as a solitary messenger from another star system was in reality a caravan of broken shards, each no bigger than a small mountain, tumbling and sublimating into the void. Astronomers labelled this process as fragmentation, an event not uncommon among comets in our solar system, but deeply disappointing when applied to an interstellar visitor. This disintegration severely limited what could be learned about its true nature. Spectral readings became muddied as the object broke into pieces. Its brightness fluctuated erratically, no longer tied to the behaviour of a coherent nucleus, but to the chaotic reflections and gas releases of dozens of smaller fragments. By the time 3I/A TLAS approached its closest point to Earth, it was effectively gone, a ghost of a comet scattered across millions of kilometres of interplanetary space. Why did it disintegrate so quickly? Astronomers have put forward several competing theories. One possibility lies in its long, lonely journey across the galaxy. Interstellar objects are ancient. 3I/A TLAS may have been travelling for millions, perhaps billions of years. During that time, repeated encounters with cosmic rays and the slow erosion of volatile ices could have left it structurally weak. By the time it reached the warmth of the Sun, its fragile crust may have been unable to handle the pressure of vaporizing gases beneath the surface. In short, it could have been a time bomb waiting for just the right trigger. Another possibility is that 3I/A TLAS had a peculiar internal composition. Perhaps its ices were unusually rich in certain volatile compounds, carbon monoxide or carbon dioxide for example, that vaporize at lower temperatures than water ice. If this were the case, then as soon as it crossed into the inner solar system, the heating may have been too much, too fast, causing violent outgassing that literally tore it apart from within. This pressure cooker effect has been observed in solar system comets before, and 3I/A TLAS may have simply been a more extreme case. Yet another theory suggests that 3I/A TLAS might not have been entirely pristine when it arrived. Some researchers believe it may have experienced close encounters with other stars during its long drift through interstellar space. A brush with a passing star could have destabilized it, cracking its surface or altering its spin. By the time it reached our Sun, those weaknesses may have compounded into total collapse. There is even speculation that its breakup may have started long before we saw it, with the process only becoming visible once sunlight lit up the fragments. In any case, its quick demise robbed humanity of what could have been a treasure trove of interstellar knowledge. What makes this especially poignant is how different 3I/A TLAS was from its predecessor, Oumuamua. Where Oumuamua had been puzzling in its shape and lack of a visible tail, 3I/A TLAS seemed more like a traditional comet, icy, bright and shedding material. Its disintegration fit that mold too, because many comets in our solar system have shared the same fate. The difference, of course, is that this one came from another star. Losing it meant losing a unique data point in our efforts to compare local comets to alien ones. Each fragment that floated away into space carried secrets we might never recover. Isotopic fingerprints, structural patterns, or even traces of exotic chemistry not found in our neighbourhood. Still, the shattered traveller taught us something, even in its death. Its breakup underscored how fragile interstellar objects may truly be, and how fleeting our opportunities to study them are. It also reinforced the urgency of preparing for the next one. By the time 3I/A TLAS disintegrated, astronomers were already discussing how to accelerate detection methods, build telescopes with wider coverage, and even design missions that could chase down these objects before they vanish. The dream of intercepting an interstellar traveller for close-up study only grew stronger. But 3I/A TLAS's story also carried a metaphorical weight. For many, it felt like a reminder of the impermanence of cosmic encounters. The universe had sent us a guest from the stars, only for it to crumble in our presence, leaving behind fragments that faded into darkness. In its shattering, it became both a disappointment and a lesson. Interstellar messengers are not only rare, they are fragile, ephemeral, and unwilling to stay long enough for us to fully understand them. Would you like me to push the next chapter even more toward the speculative and mysterious angle? For example, entertaining fringe ideas about why 3I/ATLAS broke apart, or keep it strictly within mainstream astronomy? By the time the world's telescopes confirmed the disintegration of 3I/ATLAS, the object had already begun its transformation from a singular cosmic visitor into something more ethereal, a fading spectre stretched across the black canvas of space. To the unaided eye, it was no longer visible. To professional observatories, it became a ghostly smear of dust and gas, trailing silently through the solar system like the remnants of a firework long extinguished. This ghost of an interstellar comet, as some astronomers poetically described it, was all that remained of the promising messenger that had first stirred excitement in late 2019. What had been anticipated as an extraordinary opportunity to study a coherent alien object became, in effect, a salvage operation. Scientists racing against time to collect whatever scraps of information they could before the remnants vanished forever. The debris trail itself was difficult to study. Unlike an intact cometary nucleus, which can be pinpointed and tracked with relative ease, the fragmented remains of 3I/ATLAS spread unpredictably. Tiny shards scattered over tens of thousands of kilometers, each reflecting light differently, their combined brightness flickering in ways that challenged even the most precise instruments. What astronomers could still detect, however, was the diffuse glow of dust and the faint spectral fingerprints of gas emissions. These signals allowed them to confirm that water vapor, carbon dioxide, and other volatiles were indeed present, hallmarks of a traditional comet. In that sense, 3I/ATLAS distinguished itself from Oumuamua, which had confounded scientists by showing no clear signs of such activity. Here, finally, was proof that at least some interstellar visitors behaved like the icy wanderers of our own solar system. But the limits of observation were cruelly evident. Because the fragments dispersed so quickly, astronomers lost the ability to measure the size, shape, or internal structure of the original nucleus. Spectral readings were muddied by dust, leaving only partial clarity on composition. The most tantalizing mysteries, the isotopic ratios of its elements, whether its ices contained unusual chemistry, whether it carried traces of its parent system's unique conditions, remained locked away in fragments too faint and fleeting to fully examine. In other words, 3I/ATLAS revealed just enough to tease, but not enough to answer the deepest questions. Humanity had brushed against the edge of another star system, only to find the contact dissolving in its hands. Yet, astronomers pressed on, determined to wring every last insight from the fading ghost. Some used advanced imaging techniques to track the motion of the debris cloud, hoping to reconstruct the original breakup. By calculating the velocities of the fragments, they could estimate the forces at play when the nucleus tore apart. Others focused on the dust itself, analysing how it scattered sunlight at different wavelengths. From this, they could infer the size distribution of the grains, tiny clues that hinted at how the comet had formed and what its surface might once have looked like. A handful of teams even modelled the dynamics of the debris stream, predicting how the ghostly remnants would disperse into interplanetary space, eventually becoming too faint to distinguish from the background of cosmic dust. Still, frustration lingered. The truth was that even the Hubble Space Telescope, the most powerful optical eye humanity had at the time, struggled to keep pace with the vanishing fragments. Images taken weeks apart showed fewer and fewer coherent clumps until the object was reduced to little more than a haze. Each attempt to sharpen the view only confirmed how fast it was dissolving into nothing. Astronomers were left with data sets that, while valuable, felt incomplete, like trying to reconstruct a shattered vase from a handful of dust. The irony was sharp. In a universe billions of years old, it was exceedingly rare for an interstellar traveller to wander near enough for us to see. And when one finally did, it chose to disintegrate at the very moment humanity had the instruments ready to study it. For many in the scientific community, 3I/ATLAS became a symbol of both triumph and heartbreak. The triumph lay in the fact that it was discovered at all. After Oumuamua, astronomers had pledged to be ready for the next interstellar object, and indeed they had spotted this one relatively quickly. But the heartbreak came from the realization that even preparation could not overcome the fragility of such messengers. In a sense, it underscored the enormity of the challenge. We are chasing shadows across a cosmic stage, always aware that they may vanish before we can catch them. Even so, the fading ghost was not entirely in vain. Its disintegration added a vital data point to the growing story of interstellar visitors. Where Oumuamua was mysterious in its solidity and silence, 3I/ATLAS showed us the other extreme: fragility, volatility, and a spectacular death. Between the two, a spectrum began to emerge. Interstellar travelers are not uniform but varied, perhaps as diverse as the planetary systems from which they come. The ghost of 3I/ATLAS then served as a reminder that we are only at the beginning of a much larger journey. We have seen 2 such visitors in a few short years, after centuries of none. The universe, it seems, has opened the door just a crack, offering glimpses of what lies beyond. But glimpses are not enough. The limits of observation, magnified by 3I/ATLAS's disintegration, left astronomers hungrier than ever for the next opportunity. The fading fragments passed into darkness, leaving behind no solid core, no recoverable sample, no clear answers, only the memory of a comet that had once carried the hopes of unlocking alien secrets. In the end, it was not knowledge that lingered most, but longing. Longing for the next visitor. Longing for the tools to capture it before it too became a ghost. The question of why interstellar objects like Oumuamua, Borisov, and 3I/ATLAS end up in our neighborhood is not just idle curiosity. It is at the heart of understanding how planetary systems form, evolve, and sometimes shed their material into the vast interstellar sea. To many, the appearance of these wanderers seems almost mystical, a solitary shard of ice and rock crossing the inconceivable gulf between stars, only to briefly swing through our skies before disappearing forever. But astronomy teaches us that their journeys, while extraordinary, are also inevitable. They are not chance miracles, but the byproducts of processes that happen across billions of star systems throughout the galaxy. In other words, interstellar objects come here because the galaxy is filled with them, and our solar system is simply one of many gravitational nets that occasionally snare them in passing. To understand how such fragments are born, one must look back to the chaos of early planetary formation. Every star system begins in a cloud of gas and dust, collapsing under gravity to ignite a young star. Around that star, a protoplanetary disk forms, rich with ices, minerals, and volatile compounds. Within that swirling chaos, small bodies, planetesimals, collide and accrete, sometimes merging into planets and sometimes breaking apart. But these early days are violent. Giant planets form and migrate, their immense gravity scattering debris like billiard balls. In our own solar system, Jupiter played the role of celestial bully, ejecting countless icy planetesimals into deep space during its migration billions of years ago. Many of those ejected bodies never returned. Instead, they were flung outward at escape velocity, leaving the Sun's domain entirely to drift endlessly between the stars. This process is not unique to us. In fact, it is a fundamental law of planetary dynamics. Every star with planets, especially those with gas giants, acts as both a builder and a destroyer, sculpting planetary systems, but also hurling vast numbers of smaller objects outward. The result is a galaxy littered with trillions upon trillions of such fragments, comets, asteroids, icy shards, and perhaps stranger things we have yet to classify. Each of these fragments is a castaway, a relic of its parent system's turbulent youth. They are not rare anomalies, they are the cosmic equivalent of driftwood floating in a galactic ocean. What is rare is encountering them up close, for space is vast and their density is low. Still, given enough time, some of these wanderers inevitably pass near other stars, and when they do, those stars' gravity may pull them onto new trajectories, slinging them yet again into interstellar space. When Oumuamua was discovered in 2017, astronomers realized with some astonishment that they had likely just seen the first such fragment ever identified by humans. Before then, the existence of interstellar debris was assumed but unconfirmed. Within just 2 years, Borisov, the second visitor, appeared. Then came 3I/ATLAS. 3 objects in such rapid succession suggested that our previous assumption that these visitors were so rare we might only see one in centuries was wrong. Instead, it now seems that there are billions of interstellar bodies passing through the galaxy, and it is only our limited instruments that have prevented us from spotting them until recently. The improved sensitivity of surveys like Pan-STARRS ATLAS and eventually the Vera Rubin Observatory means we are finally beginning to notice what has likely been happening all along. The galaxy is alive with traffic, and Earth is situated on a busy thoroughfare. But why here? Why our solar system? The answer lies in gravity. Our sun and its planets act as a kind of cosmic fishing net. As interstellar objects wander the galaxy, they cross paths with stars. Most pass unnoticed in the emptiness of interstellar space, but occasionally the geometry is right, and their path intersects with the gravitational sphere of a star system. When this happens, the star's gravity bends the object's path, pulling it inward. If the object comes close enough, it slingshots around the star, gaining or losing speed depending on the angle of approach. This is precisely what happened with 3I/ATLAS. Its trajectory was hyperbolic, proof that it was not bound to the sun, but only passing through. The solar system had not captured it. It had merely brushed against us, its path altered by the sun's pull before being flung back out into the galaxy. In this sense, our solar system is a transient way station, not a destination. These objects do not choose to come here, any more than driftwood chooses which shore it washes upon. Instead, their paths are determined by ancient gravitational encounters, set in motion long before humanity ever existed. Some of these encounters send them near stars, others fling them into the void. The sheer number of ejected bodies across billions of star systems ensures that, statistically, a few will always be crossing our skies. The real surprise is not that they come, it is that we are finally able to see them. The philosophical implication is profound. Every interstellar object that enters our solar system is a direct physical connection to another star system, a material fragment born light years away. It may have circled an alien sun, been sculpted by alien planets, or even carried molecules unique to its birthplace. Each is a time capsule, and when one drifts near us, it is as though another world has whispered across the void, leaving behind a small, silent relic of its existence. In this way, the presence of 3I/ATLAS and its kin reminds us that our solar system is not an island. It is part of a galactic ecosystem, exchanging matter across distances too vast to truly fathom. Of course, the frustrating part is that most of these travelers remain invisible. For every Oumuamua or 3I/ATLAS we detect, countless others slip by unseen. They are faint, fast, and often too small to catch without wide-field, high-sensitivity telescopes. As technology advances, however, our fishing net will grow finer. Instruments like the upcoming Vera Rubin Observatory are expected to revolutionize our ability to detect interstellar objects, potentially finding dozens or even hundreds over the coming decades. Each new detection will help build a statistical understanding of how common these travelers are, what they're made of, and perhaps even which kinds of star systems are most likely to send them. Thus, the answer to why interstellar objects come here is both simple and grand. They come because they are everywhere. They come because the galaxy is full of the cast-offs of planetary birth, wandering endlessly, and because our solar system, like all others, is destined to cross paths with them. They come not because we are special, but because in a universe of billions of stars and trillions of fragments, encounters are inevitable. And yet, for us on Earth, each one feels miraculous. Each one feels like a message in a bottle from across the galaxy, reminding us that in the vastness of space, we are not alone in having built worlds. The cosmos is littered with evidence of creation, and sometimes one of those pieces drifts close enough to touch the light of our sun. When astronomers first realised that 3I/A/TLAS was not bound to the Sun, their excitement was fuelled by more than just its trajectory. The true allure of interstellar visitors lies in what they carry within them, the preserved chemical and structural clues of distant solar systems. Each fragment that wanders into our skies is not merely a lump of ice and dust, it is a messenger from a world we may never otherwise touch. Unlike photons of starlight, which can only tell us about surfaces and atmospheres, these objects are solid relics. They are physical samples of alien chemistry, forged under the conditions of another star's nursery. The hope was simple but profound. If astronomers could decode the composition of 3I/A/TLAS, they could read the fingerprints of its long-lost home system. The disintegration of 3I/A/TLAS complicated matters, but even its fading fragments yielded a few valuable hints. Spectroscopic analysis revealed the unmistakable signatures of water ice and volatile gases, particularly carbon dioxide and cyanide radicals. In other words, 3I/A/TLAS behaved much like a comet from our own Oort cloud, shedding gas as sunlight warmed its icy surface. This was in sharp contrast to Oumuamua, the first interstellar visitor detected in 2017. Oumuamua showed no clear evidence of a coma or tail. Its strange acceleration suggested outgassing, but telescopes failed to capture the expected chemical fingerprints. This left scientists uncertain. Was it a dried-out cometary shard, an unusually dense asteroid, or something else entirely? By comparison, 3I/A/TLAS offered reassurance. At least some interstellar travellers looked and acted like the icy bodies we already knew. The comparison with Borisov, the second interstellar object, is even more telling. Discovered in 2019, Borisov was unmistakably a comet. It displayed a broad, clear tail and a coma rich with carbon monoxide. In fact, Borisov appeared even more volatile than most solar system comets, suggesting it may have formed in the outer reaches of its parent system, where ices are preserved at extremely low temperatures. 3I/A/TLAS, in turn, seemed to fall between these two examples. Its cometary activity was obvious but short-lived, and its rapid fragmentation hinted at an unusually fragile structure. If Oumuamua was puzzling in its silence and Borisov exuberant in its volatility, then 3I/A/TLAS was fragile and fleeting, a ghost of a comet that crumbled almost as soon as it was noticed. Taken together, these three interstellar visitors paint a picture of diversity. They remind us that not all planetary systems produce the same kinds of small bodies. Some may create dense, rocky fragments that resemble asteroids, others may form icy comets rich in exotic volatiles. Still others may produce fragile, loosely bound bodies that cannot withstand a close encounter with a new star. Each visitor is like a single puzzle piece, hinting at the larger mosaic of planetary systems across the galaxy. No two pieces look exactly alike, yet all fit into the broader story of cosmic evolution. This diversity challenges the idea that our solar system is a universal template. For centuries, astronomers assumed that the icy comets of our Oort cloud and Kuiper belt represented a standard pattern, that other systems would be broadly similar. But with only 3 confirmed interstellar visitors, we already see striking differences. Oumuamua's odd acceleration and elongated shape, Borisov's hyperactive chemistry, and 3I/A/TLAS's fragility suggest that planetary systems elsewhere are producing bodies with properties we had not fully anticipated. It is possible that their star systems contain different ratios of volatiles, different levels of radiation, or different histories of planetary migration. Those traces are enough to remind us that alien worlds are not copies of our own. Even in its ruin, 3I/A/TLAS offered a lesson in cosmic variety. Its rapid disintegration may point to a composition rich in supervolatile ices that vaporize too quickly in the sun's warmth. If so, then it could be a sign that its home system was colder than ours, perhaps orbiting a dimmer star where such ices could survive on small bodies for billions of years. Alternatively, its fragility may reflect a history of countless collisions, producing a rubble pile structure barely held together by weak gravity. That, in turn, could indicate a crowded system with violent gravitational interactions. Each theory ties 3I/ATLAS back to a different kind of stellar nursery, one unlike our own, and one that left its signature imprinted on this fleeting traveller. The implications are enormous. If 3 random visitors already show such variety, then the galaxy's population of small bodies must be even more diverse than we imagined. Each planetary system, shaped by the quirks of its star and its giant planets, is scattering billions of such fragments into the void. Some are rocky, some icy, some stable, some fragile. And once freed into interstellar space, they drift endlessly, occasionally crossing into the domain of other stars. Our solar system, then, is a crossroads, a place where these fragments converge, offering fleeting glimpses into the lives of alien worlds. For scientists, the challenge is one of opportunity. The chemical fingerprints of these objects are faint, often muddled by distance, dust, and the sheer speed with which they pass. 3I/ATLAS especially was frustrating because its shattering robbed astronomers of the chance to take high-quality readings. Yet even imperfect data reveals the truth. Alien solar systems are not monolithic. They are dynamic, diverse, and unpredictable. The galaxy is a patchwork of worlds, each producing its own unique debris. Every interstellar object that brushes our sun is a messenger from that patchwork, carrying a chemical story written in the cold of another dawn. Thus, 3I/ATLAS may be gone, its fragments dispersed into the dark. But in its short life under our watch, it gave us one more critical clue. Alongside Oumuamua and Borisov, it confirmed that the cosmos is not homogeneous. It whispered to us of the diversity of star systems, hinting that our own familiar planets and comets are just one expression among countless others. And though it slipped away, its ghost carried a message we could still read. The galaxy is full of worlds, and their fingerprints are scattered everywhere, waiting for us to learn their story. For centuries, the idea of interstellar visitors belonged more to speculation than observation. Astronomers assumed that the galaxy was filled with drifting fragments, comets and asteroids ejected from alien solar systems, but the chances of ever seeing one seemed vanishingly small. Space, after all, is vast. If such wanderers were out there, they would be faint, fast-moving, and nearly invisible against the background of stars. Many scientists quietly believed that a human lifetime might never coincide with the discovery of even a single example. Then, in the span of just 3 years, 3 such objects were spotted. Oumuamua in 2017, Borisov in 2019, and 3I/ATLAS in 2020. For a field that once prepared to wait decades, this sudden trio of discoveries was nothing short of astonishing. And with astonishment came the puzzle. Why did they appear in such rapid succession? Were we passing through a galactic stream of interstellar debris? Or had our technology finally caught up with reality? To unravel this mystery, we must first consider the statistics. Before Oumuamua, models predicted that interstellar objects should be common across the galaxy, but extremely difficult to detect. The density of these fragments, based on simulations of planetary ejection, was thought to be high, billions of them drifting between stars. Yet their small size and faint reflectivity meant that Earth-based telescopes were unlikely to see more than one per century. Oumuamua overturned that expectation. Its detection suggested that interstellar objects were not just numerous, but far more abundant near our solar system than anyone had dared to estimate. When Borisov appeared 2 years later, it reinforced that conclusion. And when 3I/ATLAS followed close behind, astronomers began to suspect something unusual might be happening. One explanation is that we are simply becoming better hunters. The past 2 decades have seen an explosion in wide-field sky surveys, especially in the hunt for near-Earth asteroids. Projects like Pan-STARRS in Hawaii and the Atlas Survey Telescope were designed to sweep the heavens for potentially hazardous rocks that might threaten our planet. In doing so, they have also become powerful tools for spotting rare, fast-moving objects that don't belong to our solar system. Oumuamua was found by Pan-STARRS, 3I/ATLAS by the ATLAS survey itself. Without these watchful eyes scanning the sky each night, both would have slipped by unnoticed. In that sense, the sudden flood of interstellar discoveries may reflect nothing more mysterious than a technological leap. For most of human history, we were blind to such visitors. Now, at last, our instruments have opened the door, and we are realizing how many were always passing through. But there is another possibility, one more tantalizing and mysterious. Some astronomers have proposed that our solar system may currently be drifting through a denser-than-average stream of interstellar debris. Much as Earth passes through the dust trails of comets each year to produce meteor showers, our entire solar system could occasionally move through galactic regions enriched with the cast-offs of other stars. These streams could be the lingering fingerprints of stellar nurseries, places where clusters of stars formed together and ejected material along similar trajectories. Over time, that debris disperses across the galaxy, but gravitational tides and star-to-star encounters may preserve coherent flows of fragments. If we are embedded in one of these cosmic streams today, then the sudden cluster of Oumuamua, Borisov, and 3I/A TLAS might not be coincidence at all. It might be the result of geography, our place in the galaxy intersecting with a river of alien relics. Testing this idea is difficult, but not impossible. Astronomers examine the incoming trajectories of each interstellar visitor, looking for patterns. So far, Oumuamua, Borisov, and 3I/A TLAS arrived from different directions, making it hard to link them to a single coherent stream. However, 3 objects are too few to form a clear statistical picture. If future interstellar objects continue to arrive in quick succession, and if their orbits align with specific galactic structures, the case for a debris stream will strengthen. Until then, the mystery remains unresolved. 3I/A TLAS isn't just another cosmic visitor. It's rewriting what we thought we knew. With NASA confirming its interstellar origin, revealing that its coma is rich in CO2, that it glows green in surprising outgassing, and that its tail is only just beginning to form, this is our clearest chance yet to witness something truly alien. It will make its closest pass to the Sun in late October 2025, reappearing in December for us Earthbound watchers. Will we be ready?